So I'm going to have a different take because I'm going to be chatting about workflows in a different domain, which is radio astronomy, and the challenges of migrating to exascale. So before I continue, I would also like to pay my respect and acknowledgement where I'm from, which is on Noongar Whadjuk country. So Nagala Kadich, Noongar Mut Kayan Kadik Nijabuja. Pay my respects to everybody's traditional owners and where they come from. And I will keep going. So radio astronomy is obviously quite a different field. We have instruments that observe the sky in radio waves. This is an example of a radio telescope that sits in a radio quiet zone in the Murchison Shire. It takes radio waves from the sky, then process it and get an image like this supernova remnant that you see in the inset, along with a bunch of other objects in the sky. This is a current telescope, but to give a context of where we're going, so one of the largest projects, science projects in the world is the Square Kilometer Array, which is the next generation radio telescope. It's a collaboration between 15 countries. There's going to be a lot of components to this radio telescope in terms of physical antennas. So it's 130,000 antennas. But there's a real complexity to integrating all this information in and then processing it and producing science results. This also happens to sit in the Murchison Shire, specifically on Inari Mana Irgar Bundara, which is also Madri Yamiji country. It's the radio quiet zone, and it happens to be, of course, because Western Australia, for the most part, most of the population is concentrated in Perth. Now, you might ask, well, what does radio astronomy offer to bioinformatics and sort of this field? Well, chatting with also one of the colleagues here, Sarah, there actually quite is a large amount of overlap. There are some differences. So radio astronomy's processing, the science processing, is very compute heavy, is very memory heavy. So we need terabytes of memory. We actually need many nodes. So if you think of compute infrastructure, a single bit of a stage of a processing actually requires many, many cores across many, many nodes. This is usually stitched together with a processing called a message passing interface, but the idea is a single task can be huge. It also can be very I/O heavy, so a single task can produce 10 terabytes to 50 terabytes, but also might have to ingest 10 to 50 terabytes. So you need really fast I/O speeds, right? So hundreds of gigabytes per second is the ideal, but tens of gigabytes, or at least that type of speed is necessary just for the incoming data. If you want to process incoming data such that you can get real-time observations, process at the same rate that you acquire data, you really require a huge amount of I/O speed. And also this workflow is data-driven, right? So if you observe a certain patch of the sky, the observations that you're trying to do, the science you're trying to get at, the data you actually collect will drive the workflow. And so it is a data-driven workflow. Now, this is just kind of a high-level overview to give you a sense of maybe what's different here. You actually have some antennas. They produce some data. The data gets initially ingested and processed. There's this process called beamforming, which is essentially just to try to understand what the instrument is seeing. So these are radio dishes. They can absorb radio waves from a variety of different angles. They tend to be focused. You want to look at a particular direction. But that also requires understanding what the response of the telescope is to the surrounding radiation field, the radio waves that are coming from the sky and all the surroundings. You then have to combine the signals from each antenna, this correlation process, and you can see in inside sort of the scale of the rate of processing you need. So it's in the teraflops per second for a correlator. Now, the idea is that, let's say for context, Cytonics, right? It's one of these it's the largest compute infrastructure in Australia. If you use all of Cytonics, you get on the order of 42 petaflops, so 42,000 teraflops per second for an entire machine. And here, processing from the ASCAP radio telescope, which is still a current generation telescope, but will be vastly outpaced by the processing that's required for the SK, is in 340 teraflops. That's to produce some initial results that then gets sent to some real compute where even more processing is required. So you have to transfer data. Sort of here, we're looking at tens of gigabits per second. We have a lot of gigabits being transferred from a remote region in Australia to the Pawsey Supercomputing Center. And then that has to get processed. So we are producing petabytes, so thousands of terabytes of data. that then gets processed to produce even more data. Usually what ends up happening is if you were ingesting a terabyte of data, you might end up producing 10 terabytes of actual science output, depending on the processing you're doing. It's not always the case. Sometimes you reduce down, but it's very data heavy and it's very compute heavy. And so this is the processing that's happening currently on Photonics, where the data then gets disseminated to scientists via virtual observatories. So you cannot download the data. Basically, the data footprints are huge. But what you can do is get spin up essentially access on compute infrastructure to then start looking at what the science is in that data set. And that will actually continue to be the norm as we go to even larger telescopes where it's too heavy to move the data around. And so the processing has to be where the data is. And so you get remote access, you do a bunch of more computing. So there's a lot of computing going on. And this is an example of an actual pipeline. So here you have some data that comes in. There's science data, there's calibration data, because you have to understand how the instrument responds. But here the idea is that you can see several different tasks that are occurring where you're going to some ingest of data, you produce a certain process, that then produces another certain process. This requires data having been processed to produce some calibration, and it goes forward. And it looks normally, at least for this particular sort of workflow, straightforward, but the idea is that to remember that there's a lot of compute. You need a lot of computing to do every single task. Some tasks will finish faster than others, and also some beams, so some particular antennas, will complete faster than others. So there's a lot of asynchronous processing that's happening here. Eventually, you might then aggregate all the results and produce some interesting science. And that's the rough sort of simplistic workflow. And the idea here is then again, the resource footprint of each individual task here, right? The amount of compute can vary by quite a bit. So in this case, right, we're looking at very HPC heavy workflows, so very high performance computing, heavy computing workflows, where a single task might need a few thousand cores to do some processing, where there's some reading and writing of terabytes of data. And another particular process might take 5 minutes and use a single core. And so this massive amount of heterogeneity in the task, the resource footprint of a task is very tricky. And there's also usually a lot of I/O stitching all of this stuff together with lots of possible large file writes. So you really need distributed, fast, parallel file systems. And some need lots of small files. So they'll write like 1 million files. So that is also a challenge. And all of this is impacted by what is actually being observed. So if you observe a patch of sky and you're trying to do some observations and a satellite goes in front of the radio telescope, that satellite will produce radio waves. Those radio waves will be much louder than the radio waves from more distant objects that you're trying to look at in the sky. And suddenly your workflow will say, well, this bit of data is terrible, or at least perhaps this antenna has seen something that's terrible. I need to chuck it. It's not useful to go through further science processing, but other ones might. So you get a lot of complexity in terms of the footprint and the time, right? So here's an example of a job dependency for a particular bit of processing. You can see that the hierarchy of tasks that need to happen, and also sort of the resource footprint, is varying quite a bit. So the resource footprint is kind of given by the scale of the circle. This is quite a complex acyclic graph or DAG, but it's a job dependency tree, right? You can see that there's a huge amount of complexity here, and this is just to produce a particular science output, and there's a lot of variety here. So very similar to maybe some of the challenges that bioinformatics faces, it just can get quite complex, and this can be a real challenge for a supercomputing center like Pawsey. So I want to give some context, and I want to start a conversation. The focus for radio astronomy for the large portion of its existence has been getting performance, because the task can be so compute heavy, memory heavy. So the organic growth of trying to organize this type of workflow has been done through Bash script and Slurm. So Slurm is a job scheduler for HPC centers, high performance computing centers, but it's not kind of suited to this type of complexity of workflow. And the complexity is just increasing. So as an HPC center before, we were, people were pretty happy just having essentially scripts, and the job orchestration tool being Slurm as perfectly valid way forward. But now it's becoming a real challenge. And so there's real work to try to integrate some stuff like Nextflow, just heard of Nextflow, or Prepict to improve current pipelines. But there's a huge amount of technical debt, so it's a real challenge. But there's also a unique HPC challenge, right? This is very HPC oriented, so very compute heavy, memory heavy bits of workflow where terabytes of data are produced. Lots of CPUs need to be run, lots of GPUs need to be used to produce some science products. If you think of also a shared file system, if you took all the bioinformatics workflows and tried to run them all concurrently on an HPC system, they're all sharing the same I/O system. And the same job schedule. And that's a huge issue when we also consider computing resources going forward. If it's AWS and you're isolated, you're not sharing those resources, but we have shared resources. So this idea of producing files and lots of metadata queries actually can really slow the I/O performance and can negatively impact all users on the system. You can have a large number of files being produced being a huge challenge, and also performance. As we go to, as Suresh mentioned, even larger workflows, the idea of writing a file is super slow compared to keeping it in memory and having things chat to each other, streaming data between memory and never writing to the file system. Because that can really improve speed. But then that's a challenge of like restarting a workflow or trying to extract as necessary given circumstances of when to write a file. So going forward, we really kind of need a holistic approach for the workflows because you need exascale workflows and exascale codes. And the exascale workflow is not about being able to completely consume the system, but dynamically consume portions of the system as best as it can, reacting to what others happening. Because if we have everybody use as much as they can, the system will go down, at least for supercomputing centers. So I'm just going to put in my questions, right, which is a conversation I'm having with the radio astronomy group as to how to guide researchers to an optical workflow tool, given the hardware they're going to run on, and given also their workflow, right? The other thing is how to test the scaling of a workflow, because some of the stuff doesn't crop up till you hit an enormous amount of scale. If you try to submit 10,000 workflow jobs, then you really start maybe stressing the system, but maybe 600 is okay. So people were running stuff at 600 and then just naively tried to scale it and then hit a huge amount of issues trying to scale. And I would love to know how various communities are addressing the challenge of massive data-driven workflows, because it is actually quite a unique challenge of also restarting workflows. If they fail, how do you account for failures? All right, you have shared resources. Essentially, what is the conversation going to be? And on that, I will end with your questions. And I tried to keep it short because I wanted to have a conversation kind of progress.